Do you want to excel in maths and science? If your answer is yes, then let me tell you, go ahead with Infinity Learn courses. And to get best discounts, subscribe right now. The link is given below in the description. Hello my dear students, welcome to my channel. And as you all know that I am Divya, your science expert. And today in this session, I am going to talk about very interesting topic from your subject chemistry. And the topic is taken from chapter chemical bonding. So basically, we are going to discuss about topic VSEPR theory, that is valence shell electron pair repulsion theory. But before we move ahead, I would really like to share with my students that when you buy the course, then you can use this coupon code DE10 to avail extra 10% discount. So hurry up, purchase the course and use this coupon code DE10. Okay, now let's start with VSEPR theory. So VSEPR theory means valence shell electron pair repulsion theory, right? This theory is basically given by two scientists, Sidgwick and Powell, in 1940. Now, what forms the basis of this theory? Let's study about it. See, we know that whenever a molecule is formed, or if we say whenever an atom tries to bind with some other atom, we know that only valence electrons participate. Right? Whenever an atom tries to bond with some other atom, only the valence electrons are the one which participate in the bond formation. Right? Now we know that, like if I say about nitrogen has got 7 electrons in total, and the electronic configuration is 2,5. So it is having 5 electrons in its valence shell, right? And we know that all the electrons, they are negatively charged. So what happens that whenever some atom comes to bind with nitrogen, what they do, they repel the electrons. They repel the electrons of that, or you can say they repel the incoming electrons, right? So basically there is a repulsive interaction of the valence electrons within the valence electrons of same atom, and also with the electrons of incoming atom. Right? Now we know that there are two types of valence electrons which we usually come across. The electrons which participate in the bond formation, the valence electrons which participate in the bond formation, they are called as bond pairs, right? And the valence electrons which doesn't participate in the bond formation, they are called as lone pairs. Right? But both of them, they are negatively charged. They have a negative electron cloud. So obviously they will repel the incoming electron. So these repulsive interactions are not good, for a molecule, because they will not let the molecule to be stable. We know that whenever the repulsive forces are more, that means the molecule tend to occupy a state of more energy, and more energy means less stability, right? So repulsive forces are not at all good for the formation of a molecule. So what happens, the valence electron of that particular atom, they arrange themselves in such a way so that the repulsions are minimized, right? That is they don't force more repulsive forces on the incoming electron, and the molecule which is formed is stable. That is, it has the state of maximum stability and minimum energy. So this whole thing that we have discussed form the basis of VSEPR theory. I hope you got it. I'll repeat once again. We know that valence electrons, they participate in the bond formation. So there are all the valence electrons, they are negative, they have negative cloud, whether they are bond pairs or they are lone pairs. So they tend to repel the incoming electrons. Those repulsive forces will increase the energy, and the molecule will tend to occupy the state of minimum stability and more energy. So you can tell about it if somebody asks you about that on what basis the VSPR theory is formulated. You can say that only the valence electrons participate in the bond formation, and the bonded atoms around central atom, they suffer repulsions, due to more repulsive forces, they acquire the state of minimum repulsions and maximum stability. That is, the valence electron tend to occupy such positions where the repulsions can be minimized and the stability can be maximized. So basically, okay, I think you understood about lone pairs and bond pairs. So still I want you to tell me, you can see this molecule. Can you tell me about the bond pairs and lone pairs which you can see in this? Yes, you are right. These are bond pairs because these pair of electrons are used in bonding, and this pair that you can see is a lone pair because it is not participating in the bond formation, right? So we know that whenever a molecule is formed, if it has all the bond pairs, then also the repulsions would be there, and if it has all bond pairs along with the lone pairs, still it will have repulsions, but the strength of repulsions will differ. We are going to discuss later about it. Okay, now let's have a look on the postulates of VSPR theory. Right? So the first postulate states that the shape of the molecule depends upon number of valence electron pairs. It is correct that whatever will be the shape of the molecule, that depends upon the valence electrons. Right? For example, if I talk about carbon, we know that carbon has got 4 valence electrons. So these electrons, they will also repel each other. So they tend to occupy such position around a central atom where their repulsions are minimized. Okay, and if let's say this carbon tries to bond with hydrogen, then the electrons of those hydrogens will also arrange them in such a way so that the repulsions are minimized and stability is increased. So they arrange them in such a manner. So whether we have bond pairs or we have lone pairs, they all are responsible for the shape of the molecule. Now you can see this one, NH3. See, it has got lone pair also. So the position of the electron pairs and lone pairs is such that it is giving giving a shape of the molecule, and the shape is decided in such a way that where the repulsions are minimum and stability is maximized. Okay, so the electron pairs, they occupy the position so as to minimize repulsion. I hope you got it. So shape of the molecule will always depend upon the valence shell electron pairs, whether they are bonded pairs or they are lone pairs. Second postulate says that electron pairs in valence shell, they also tend to repel each other. So for example, if I make the electrons, valence electrons, as a denote around a central atom, so you arrange them in such a way. Why? Because these pairs are also repelling each other. So that is why they tend to occupy such position where the repulsions get minimized. Okay, another postulate, electron pairs tend to stay as far as possible so that the repulsions are minimized. Again, I told you that electron pairs, they arrange themselves in such a way where the repulsive forces are least. Right? Like you can see this molecule. Here you can see that one atom is here, one is here, and one is here. And these are the electron pairs. See how they have arranged themselves. Okay. Another postulate is that if you take a valence shell is taken as a sphere. For example, if I talk about carbon, let me tell you that valence electrons are arranged around carbon in such a way. So if I imagine it as a sphere, right, then we see that the position of the electrons, they are localized. This is a hypothetical, postulate, but still it is assumed that the position of electrolyte around a central atom, it is always electrolytes. That is, the electrons they tend to occupy fixed positions. And if in case we have any multiple bonds in the molecule, for example, if you talk about carbon dioxide, it has got a multiple bonds. Here you can say that it has double covalent bond, and even it has a double covalent bond, but it is taken as a single unit. It is counted as a single unit. So all the double bond and the triple bond existing at a particular place is taken as a single unit. Now we have already discussed that a molecule may have all bond pairs or may have bond pair along with the lone pair. So let me tell you about the repulsions, repulsive forces, right, they have. So lone pair repulsion is maximum, right, and lone pair bond pair repulsion is less than the lone pair and lone pair repulsions, and least repulsions occur when there are all the bond pairs. So bond pair repulsion is least as compared to the like it is lesser than lone pair bond pair repulsion, and the maximum is exhibited by lone pair repulsion. And you know that these repulsions actually decide the positions of the combining atoms. They decide the bond angle basically. So we have seen that the repulsive forces decrease. Obviously they will decrease if the distance between bonded atom increase, right? Therefore the bond angle increase. You must have seen like there are few molecules which have different angles. For example, if I say I have a molecule which has 90-degree bond angle, maybe another one 120 degree, and maybe another 180 degree. So obviously repulsions will be least in 180 because they are as far as they can be, right? They are maximum far in this case, right? So as the bond angle increase, obviously the repulsive forces between them decrease because distance is increasing. Now if the central atom of a molecule is surrounded by all the bond pairs, then asymmetrical shape of the molecule can be expected. But if it has lone pair also and bond pair also, then in that case there would be lone pair bond pair repulsion also along with bond pair, right? So the molecule would tend to have distorted shape. This means that the shape will be actually distorted from the original one. Distorted means it will slightly change. The bond angle will change because in that case the repulsion between lone pair and bond pair will also comes into notice, and we know that lone pair bond pair repulsion is always more than bond pair repulsion, right? So if all the pairs are bond pairs, then it is going to have a asymmetrical shape like in this. But if it has lone pair also, then you will see that the geometry gets distorted. Otherwise it should be like this. If there are one central atom and three linked atoms, the geometry should be like this. But here in this case it has got three atoms, but along with it it has lone pair also. That is the reason the shape got distorted, because lone pair bond pair repulsion also comes into play. Okay, now how many lone pairs or how many bond pairs are present, or what is the magnitude of the repulsions between lone pair and bond pair, that decides the geometry of the molecule. Now how can we define the geometry of a molecule? Like this is the geometry of BF3. So basically geometry means that is the relative arrangement of bonded atoms in a molecule, or in a way such that the bonded atoms direct themselves around the central atom in such a way that they impart stability to a molecule, right? So this is particularly called as geometry. Like a geometry of BF3 is this, and geometry of NH3 is this, because when these molecules are actually representing the accurate position of the atoms where the repulsions are minimized and stability is maximized. Now on the basis of VSEPR theory, like we know that any molecule may have only the bond pairs, and if along with it has lone pairs, then the geometry get distorted. So this chart actually shows where the molecule has all the bond pairs, right? So if two combining atoms are linked with the central atom, the geometry is linear somehow like this. Right? And if it is three atoms which are combined to central atom, the geometry is trigonal planar. For 4 it is tetrahedral, 5 is trigonal bipyramidal, 6 is octahedral, and 7 is pentagonal bipyramidal. But in this case all of them are bond pairs. They don't have lone pairs. But if in case the lone pairs are present, they may be 1 in number, maybe 2 in number, maybe 3 in number, or maybe 4 in number. So accordingly the geometry get distorted. Okay, for example, let's discuss this chart on the basis of VSEPR theory. If there are two combining atoms, right, with no lone pair, then the geometry is linear. This is how, the combining atoms will arrange themselves around the central atom. Now, if it has three atoms linked to a central atom with no lone pair, then the geometry would be trigonal planar. And if it has one lone pair, then the geometry will get distorted and it will be something like this, and distorted trigonal planar would be called as bent. Now, if there are four combining atoms around a central atom with no lone pair, they will arrange themselves in this way. It is called as tetrahedral geometry. But if it has one lone pair, it gets distorted, and it's the special name for distorted tetrahedral with one lone pair is trigonal pyramidal, and with two lone pairs it will be called as bent. So they have special names. When they get distorted, they have special names, and you have to learn all these names. Same way, if five surrounding atom around the central atom, then with no lone pair, then the geometry would be trigonal bipyramidal. But if it has one lone pair, geometry gets distorted and we call it as sawhorse. And if two lone pairs, it is called as T-shaped, and with three lone pairs, it is called as all of them can be called as distorted trigonal bipyramidal, but you have to learn their special names as well. So we call it as linear. Now, six surrounding atoms around a central atom, the geometry is like this, octahedral with no lone pairs. But if it has one, it is called as square pyramidal. And if it has two, it's square planar. If it has three, then T-shaped. And if it has four, then again it is called as linear. So I hope you understood that how the presence of lone pair distort the geometry from the regular geometry, right? And the reason being that lone pair bond pair repulsion is more than the bond pair repulsions. And even if a molecule has more than one lone pair, then in that case lone pair repulsion also comes into notice, which is maximum. So this is how, on the basis of VSEPR theory, we can tell about the geometry of different molecules when they have no lone pairs or when they have 1, 2 or 3 or 4 lone pairs around them. But see, every theory has certain limitations too. So this theory also has a limitation, like it doesn't tell us about the bond parameters. That is the directional nature, bond angle, repulsions, etc. And these limitations were covered by another theory, and we'll be discussing that theory in the next class. So thank you, take care, bye-bye. I hope you have understood the concept, whatever I have taught you. My one request to you, if you haven't subscribed my channel, then just subscribe it right now. And any doubts if you have, you can always write it down in the comment section. Thank you, take care, bye-bye.